I need to get us going to our last speaker for this session, which is Ryan Fisher from Christopher Newport University, which is Fun with Fourier Transforms, or How I Learned to Stop Worrying and Love Convolutions.
Hi, everybody. I'll share my screen. There we go. And put this in the slideshow mode. All right, can everybody see it okay?
Mm-hmm.
Okay, so thank you for having me today. My name is Ryan Fisher. I'm from Christopher Newport University. And so I've been there for about, well, over 3 years now. With the pandemic, I haven't gotten to attend many of these things, but I'm glad to be here now. So nice to meet y'all. I used to attend a lot of these up where I was in Syracuse before here. So I used to attend a lot of these kind of meetings up there. So glad to be here. So goal of the talk today is just instead of talking about what I do with LIGO so much, I'll just glean on that, but to do something more fun, present Fourier transforms in an accessible way without getting bogged down in the math, and give you some fun and interesting ways to motivate your students to love Fourier transforms as much as I do is the point of this talk. Just more of a fun, lighthearted talk. So what is a Fourier transform? You can sit down and write down the integrals and go through all the calculus and kind of talk about it in that way. But instead, what I'm going to do is I'm going to talk about, we're going to hop right to the other way of looking at this, which is to talk to your students about how you kind of take a function and decompose it into a function of something else. But instead to talk about it as something they really understand, which is on the left, we're just going to plot a sound wave, a function with an amplitude that goes up and down as a function of time. And then on the right, we're going to plot the same thing, but we're going to plot which key you press on the piano. Now, ignore the left side of that plot, of course. We tell our students just take everything on the positive axis and think about that. And if you push a different key on the piano, you get a different wave on the left. And that's pretty much the idea that I like to just kind of introduce these with, is say, okay, just think about that correlation between which key you push on the piano is the frequency that you get on the right plot, and the wave you get on the left plot corresponds to that frequency. Mm-hmm. So then I can also tell them, hey, what else is a Fourier transform? Well, you don't have to do all this math if you don't want to. If you're in two-dimensional space, you can just let nature take a Fourier transform for you. And this one's kind of fun. Just shine light through an aperture of the right shape. So a good example is if you take a circular aperture and you shine light through it. So you take a laser light, shine through a circular aperture, you get this pattern on the bottom right. And this is a laser going through a small hole, you get an airy disk. And that's just the Fourier transform of the two-dimensional spatial circle. Getting some feedback. Okay. So then if we think about that Fourier transform, what is it? It's taking one function, a function of shape or position, and converting it into another function, a function of angle. And so I can tell you from personal experience, you can get past 50% of a radio astronomy class just by knowing this one formula that comes out of that. Theta equals lambda over d. I went to University of Maryland. I literally got 50% on the first exam by just using that equation over and over. So there you go. So the resolution angle, what that means is correlated to the wavelength over the diameter.
You will be required to provide your verbal password.
So I think it's
if you do not have your password, you can find it on your myatt.com account under account profile on the left.
Behzad Magami, I think you're the one who had, there we go.
Thank you.
Thank you.
Okay, right. So you send the light through the small hole, you get a Fourier transform of that whole shape, which is pretty fun to do and show your students. The other cool thing about this is if you're actually using a telescope, which is actually just a hole in some sense if you think about it in space, but a dish is kind of like a hole in space. You send two stars into that telescope and you want to be able to see the two stars on the output. Well, you have to make sure that they don't overlap in these images that you get. So I'll come back to that in a minute. So with great power comes great responsibility. Fourier transforms are super powerful, but just make sure you don't accidentally take the Fourier transform of your cat, right? So this is an ex-KCD comic. Randall Munroe was one of the alumni at CNU, so we like using their comics. So this is a fun one. Okay, so power of Fourier transforms in 10 seconds. They're useful in many contexts. Great in astronomy for deconvolving things and getting a tiny source amongst other louder sources nearby. Great in trying to analyze the noise in the detector. Again, you take the spectrogram here, time on the x-axis, frequency on the y-axis. You have finding a tiny signal buried in really loud noise. They're great for that too. And they're also great for helping you determine the difference between a picture of a cat and a dog, which I'll come back to too. Okay, so I like this one a lot as a way to introduce this to students because I want to talk about Fourier transforms, but I want to really motivate them. And the point is, I'm going to say convolution is one of the best uses of Fourier transforms. But what the heck is convolution and who uses that? Well, here's an example. Let's say you have a sound of a dog. Okay, can everybody hear the bark? Does it work through the audio?
Mm-hmm.
Yeah, okay. And then you have a sound of somebody snapping in a concert hall. Let's play that again. Okay. And then if you convolve those two sounds, you get something cool. And note, I did not put a dog in a concert hall. All I did was convolve those two sound files, right? And so you can take any audio you want and manipulate it using convolutions to make it sound like something is in a different environment. I used to have a radio that would do this. You could put yourself in a concert hall or inside a car. You can make it sound like you're in a different place. And the other thing is if you start with this and you don't want all those echoes, well, all you have to do is go to your concert hall, snap, get that sound, and deconvolve to get back to the sound of the dog. So you can take the echoes out of your signal. So that's audio synthesis. Oops, lots of barking. Okay, all right, so this is like phenomenal cosmic power now, right? We can take a Fourier transform to do this horribly complicated thing called convolution. And that's what this tells you. But again, skipping the math, the whole point of this is convolutions are this nasty integral on the top right. But in Fourier land, in the Fourier domain, it's just a multiplication of two functions, which is practically trivial. Just to show you how trivial, if I have a signal of length to the m, and m is going down on this table, the difference between doing the Fourier transform and the direct convolution ends up being 262 times faster by the time you get to m equals 15. And it just gets worse and worse. So deconvolution, convolution, way faster with the Fourier transform. And that's why it's so powerful. So here's that cat example again. If you're going to take the Fourier transform of your cat, don't do that. Take the Fourier transform of the image of your cat, and you can do something useful with that. So what you can do is you can do something called image recognition. This uses convolutional neural networks, again, that word convolve. So you use all the pixel values in an image, but you convolve that image with many different filters to get another different image of your cat. And you let the neural network pick which filters are the best in the end, but the goal is you have to do that convolution over and over and over with many different filters. So let's look at what that looks like. So there's your cat convolved with a ton of different filters in the top right, and you can see how each filter picks out different kind of features of the cat. And then in total, you do the same thing with your dog on the bottom right, so that's where that picture of the dog came before, and you get some different filters and some different features for the dog. And without this pre-filtering step, it's extremely difficult to get artificial intelligence to determine the difference between a picture of a cat and a dog. But as soon as you do this pre-filtering, this convolution, now it's like 99.9% of the time the neural network can determine the difference between a cat and a dog. So that's really cool, but the takeaway of this, I think, is also that dogs are obviously cooler, given the color scheme, of course. Okay, all right, so here's the gravitational wave example. We're gonna dive into this for a second. In our research, we're trying to find a tiny signal buried in a gigantic amount of noise. The tiny signal has been amplified a ton on this picture. Blue is the signal, that's the gravitational wave. Here's noise, and you can see the noise is relatively loud. And then time is on the x-axis. Now ignore the scale on the y-axis for a moment. What we do is we do a thing called match filtering, which I don't know if this bubbles on your screen, but I'll make sure I move it. Match filtering is that integration on the top right. Already we've converted into the frequency domain, which means we've already taken a Fourier transform, and then we're doing a multiplication, right? So we've done that Fourier transform, we're doing the multiplication. This is really in the time domain a convolution. So I'll show you the convolution in a graph. Watch the GIF for a sec. What you're doing is you're taking an expected signal and you're multiplying it by the data, and then you're looking at the result for each point in time, and then you're sliding it in time. So that's a convolution in time, you're sliding in time. And what you get out is that when the expected signal and the real signal overlap, you get a huge SNR, a huge signal to noise ratio. So it's a great way to use Fourier transforms and convolution to dig a quiet signal out of your data. And that's how all of LIGO analysis works, looking for gravitational waves when you're looking for quiet signals that you know the shape of them. Another way to look at that for physicists or mathematicians is you're projecting the data onto the signal vector, and noise projected on the signal gives you a small number, where signal projected on the signal gives you a big number. So we can compare them and the signal pops out. Okay, so that's a really powerful way to use these. One other cool way to use these is take a look at the image from your telescope. That's a star on the bottom right from Hubble when Hubble was broken, basically. A single point source star should be a dot, but in fact, that's what the star looked like with the not so great optics. If you had a perfectly circular aperture, it would still not look much better than our thing on the left there, which is the airy disk, because perfectly circular aperture under Fourier transform looks like this disk. But on the right, that's what it really looks like. And you kind of see the airy disk in there, but there's a lot more going on. So that's a pretty extreme example with flawed optics. Let's take a look at what you can do with our convolution methods. Well, we call that thing, that spread out image, the point spread function of our telescope. And let's say you take a couple objects like that on the top of this picture here, these two stars, and you send them into the light into your telescope. Well, your telescope spreads that light out. And really what's happening is it's convolving those two images effectively, those two images on the left. And you get your final image, which is the image you see on your CCD of your telescope on the right. Of course, you have to take into pixelization, but aside from the pixelization, that's basically what you get. Now, what if you wanted to get the top left picture, which is the real light coming from the stars? How do you get that back? Well, in Fourier land, it's just division. You just divide your image by the point spread function, and you get back that nice pretty image, a nice pretty picture on the top left, that nice clear object image. And so here's a great example of that being done in real life. On the left is a blurry image from Hubble. And then you deconvolve with that point spread function, which you can just literally take a picture of any point source and take that as your point spread function. And you deconvolve, and then you get this on the right, which when deconvolve, it means you take the Fourier transform, divide, and then take the Fourier transform back to get the image you want. And so you can see this supernova remnant really pops out when you do that deconvolution. So these are a whole bunch of ways to motivate your students to love Fourier transforms as much as I do. I have a bunch more. Also, fixing your instrument helps. Here's raw Hubble data before and after they fix the optics, and you can see just how much better it is. But you can still go even further then by using the deconvolution of the point spread function. So I don't know exactly how much time I started with because last talk was a little over. I have some extra slides if there's time, but if anybody wants to contact me, there's my email. If you have any student interest in gravitational waves, please send them my way. Let them know my email, and I'd love to talk to them. And I love giving talks about all things gravitational waves, astronomy, and physics. And then I have more slides if you'd like, or I can do questions up to the moderator. Thanks.
I think I would like to make sure that everyone who has a question about what you've already presented has the opportunity to do so. And then if people decide they'd like you to continue, then I think we can do that.
Sure.
So I will open it for questions, and then if we don't have any, we'll give you that time.
Will we be able to obtain today's meeting? Will it be on the CSAAPT website?
Tatsu is the best to answer that.
That is the plan. We plan to put all the slides on the CSAAPT website. So, so speakers, I'll be emailing you all to collect the slides. Thank you.
Rachel looks like she has a question. Or Rochelle? Yeah.
Rachel. Thanks.
Okay.
Yeah, this is really cool talk. I love talking to my students about how cool Fourier transforms are. But when I go to actually teach it, I end up using only very when I have them play around with it, I use only very pretty perfect examples. And I was wondering if you had any really easy to use tools to for students to play with without having to, implement a fast Fourier transform, or what do you use when you're introducing this in a classroom?
Yeah, so I mean, I like to use two things. One of them I like to use is a set of Jupyter notebooks. Basically, you just pop open a Jupyter notebook. Now, again, I have the advantage of being part of a giant collaboration where I can just pop open a Jupyter server that's not even mine and just start opening Jupyter notebooks that have everything installed. But you can, if you have a Jupyter server set up, you can install some packages that already have this and just have, some pre-built notebooks ahead of time that show them, okay, here's some data that we get, just take the Fourier transform and show what it looks like. But the good examples, I really like to show the good visual examples, like just show them the basic ones, like the Fourier transform of a top hat makes a sink. Fourier transform of a comb makes another different comb, right? Show them those basics, and then show them like the power of like convolution. You convolve two top hats in time, that gives you a triangle, but in the frequency domain, it's just a sink squared, right? You just show them that combination. And I think by like showing them the repeated visuals of like the time domain, the Fourier domain, it starts to click. Like, and honestly, in my research, when I'm analyzing noise in our detectors, I like try and do that in my head. I'm saying, okay, which two functions were convolved to make this horrible noise that I'm looking at, right? Which two things? And so like maybe going back to, oh, right, I'm not sharing my slides anymore, but there's something like a repeating sort of like arch shape. Well, that repeating arch shape means, okay, that arch is caused by, maybe it's part of a sine wave multiplied by top hat, right? You can think about what would have caused that in the time domain, and then go look for it, right? And try and look for what's causing that kind of shape. So that's kind of how I work through it with them, especially in my research group. I often do that kind of stuff where I'm like, okay, this looks like a comb multiplied by something, right? And try and get them used to that practice of it. But I think the Jupyter notebook with a standard package. We have a package that's open in LIGO. It's called this. It's just called GWPy. And there's like a great set of examples, right? That's okay. I love dogs. Don't worry about it. So yeah, so there's a great set of examples for GWPy. If you just search that on Google, GWPy Python package, you can install it. It will install everything you need, and then you can just run a whole bunch of the demonstration examples, and you can like plot a gravitation wave, then plot the spectrum of the gravitation wave really quickly in like 3 lines. So it's really powerful to show things. That is a real example if you want. So that's a good one.
Ryan?
Yes.
I use I just try to introduce my students, university students, to Fourier transforms, and I use the PhET simulation called Fourier analysis. You're probably familiar with that. Yeah, it's pretty good. You know,
use those all the time. Yeah.
Heavy math, so I like that as an introduction. But some students aren't really interested, so I think your talk, maybe I could find a better way of introducing it, just better applications than just trying to break down a square wave. You know,
yeah,
not so interesting.
That's the whole thing. Like, you got to get them motivated, right? And that's why I'm always trying to do. I mean, just like that very first talk today by let's see, I think it was Leah. I'm sorry, I can't remember the last name, but yeah, that very first talk was the thing. Like, get them motivated first, and then have them go ahead and dive into the math, right? And make it exciting, not fearful, like this horrible integral, right? Yep, that's the point of this. Yep.
Thank you.
I know there's another question in the chat, but I also know we need to transition to our second session.
Yes, sorry, Dr. Fisher. I'm sorry, my microphone was on at the beginning.
Oh, no,
sorry for that.
You're all good. It's just par for the course at this point. You're okay.